Please.
I see. Now I got it.
Sorry, please.
Yeah. Again, good morning, everyone. I'm Zeynep. I'm sorry that I cannot be there. My mentee Ulaş is the first speaker of this, I don't know, sunny, very hot morning. He's a senior student at Boğaziçi University. He's currently doing an industry internship at Pegasus Airlines. He's actually very good at coding, and he's planning to apply a master's program this year. So if you have a position or if you have a suggestion for him, please, reach out. With him, we studied some machine learning methods, specifically the classification problem. As you all probably have heard, we are in this era of big data, and we need some automated methods to analyze it, right? And machine learning is actually the set of methods that can learn regularities and patterns in the observed data, and then use them to make accurate decisions about the unobserved data. So now, Ulaş, the stage is yours. You're gonna talk about the technicalities.
Okay. Well, we will talk about machine learning method today, and I want to thank Zeynep and also the RP organizers for providing us this opportunity. Now, before diving into machine learning methods, we need to get familiar with some definitions. The first one is the feature. Features are a set of attributes represented as a vector. So, and as an example, a feature can consist of person's height, weight, or gender. So as you can see, a feature can include continuous and discrete variables. And we call the discrete ones categorical and continuous ones quantitative variables. And the other definition we need is the label. And labels are categories, values, or ordering in a label space assigned to our example or features. And there are also two types of labels. One of them is classification labels, and the other one is regression. And we will use only classification labels in those slides. Now, we have features and labels now, and our data set is ready, but we need to split our data set in two sets. One of them is training set, and another one is test set. As their name suggests, we train our algorithms with training sets, we test with the test set. Now, and actually I told a lie, because we don't have the labels all the time, which is called unsupervised learning. You can think of it like students sitting on the grass. We can deduce that who are friends from their sitting arrangements without knowing the group names. And the other one is supervised learning, which we'll use it through the slides. Well, supervised learning is the opposite of unsupervised learning. We have the labels now. And just one ingredient left for diving into machine learning, which is the loss function. Well, loss function is a method for evaluating our model. If the output is higher number, it's saying that our model doesn't work very well. And if the output is a lower number, it's saying that our model works pretty good. And there is not just one loss function actually. So there are a lot of them, but we will use just likelihood loss function in those slides. Well, what likelihood does is that the likelihood loss function takes the probabilities our model gives us and just multiplies them. Now we are ready to diving into our first machine learning method, which is Gaussian discriminant analysis. Well, we have an assumption here, which is that the training data we have are distributed with respect to normal distributions. So we are trying to find the class which maximizes this equation now. Okay. And if we open up this probability function, we will end up with this ugly looking function. But if we investigate a little bit, we see that the third term and second term doesn't depend on our features. So just ignore them for now and just focus on the first term. Well, it looks like a distance function actually. If the covariance matrix is identity, we see that it gives us the distance from our test sample to mean of the class. So the role of the sigma is here, it transforms the common distance function to weighted distance function. Okay, so the actually QDA, which stands for quadratic discriminant analysis, just maps the x to the closest mean. Okay, now we have two images now, and you can see these black lines. The black lines are decision boundaries. So the decisions boundary is where the probability of being blue and red is equal. So, and we will actually end up with this parabolic line all the time with quadratic discriminant analysis, QDA, but sometimes we will end up with the straight line. Well, the straight line occurs when the covariance matrices of all the classes are the same. And we will investigate this straight line. How do we get it? And again, if the covariance matrices of all the classes are the same, we can do some simplifications and rearrangements in our probability function. And if we do that, we will end up with an equation. Just the first term is the projection equation now, and the second term is just class dependent constant now. Okay, now all we need to do now to determine which class our data belongs to, just look at the comparison below. And if we do the rearrangements again, and if one can define the mu hat and W just in this block, the equation becomes just the projection now. Well, to get the intuition, if we add some further assumptions, like if the covariance matrices is identity and probability of being red and blue is equal, if we don't have any information, then the equation now simply informs us which classes mean the data is closer to. Well, so our decision boundary, if we say that the mu1 is the mean of the red points and mu0 is the 0 points, the decision boundary will be perpendicular to this blue line and also pass on to mu hat. So it will consist of the points, the distance to mu0 and mu1 is equal. Okay, the final part of Gaussian discriminant analysis is learning the parameters. So how do we know the mean of the red points, or how do we know the covariance matrices of the blue points? Well, actually, we don't know the exact form, but we estimate that with just straightforward equations, but with straightforward calculations now. And our calculations based on the maximum likelihood estimations. So the probability of being red is actually the total number of red points over the total number of the points. And the mean of the red point is just the center of mass of the red points. And if you are familiar with the covariance matrices equation, how do we calculate them? It is just this. And if we need to work with LDA, linear discriminant analysis, so we suppose that the covariance matrices is equal, well, then we just take the mean of the covariance matrices of all the classes. Now, we are ready to discuss another algorithm, which is KNN algorithm. Well, in KNN algorithm, we need just two ingredients to specify the classifier. One is K, the number of neighbors, and the other one, the distance function, the measure of nearness. Well, how does it work is that it calculates the distances and choose the K nearest neighbors from it, and looks at the majority points. I mean, okay, we will see an animation after, and then make a decision. Now, we have an animation. Okay, this is our training sample, and this is our test sample. It gets the distances, and then choose the nearest 15 of them. So K is set up to 15 in this slide. And sees that the majority of the points is blue, so it decided to be blue. And now again, it takes the distances, choose the nearest 15 points, and sees that most of the points are red, so it decided to be red. And again, the same thing for the Korean region. Okay, so we see that, and I trained this algorithm with this training data, and we see that our model splits the plane in three regions: red, yellow, and blue. And we see the probabilities of being blue, red, and yellow in the below images. Well, in the yellow parts, the probabilities are very high, and in the blue parts, the probabilities are very low. So one can ask now, why don't we use every time, since we are actually looking at the common features? Well, there is unfortunately there is a crucial part, which is the dimension. Well, we see that in higher dimensions, the points can be far from each other very easily. What I mean from that is that if we see that example, okay, suppose we have a training sample now, which lives in the 20-dimensional space, and the data points are distributed uniformly in this unit sphere in 20-dimensional space, and we just want to take 1% of our data to decide which class or sample is. And if we do the calculations, we see that the distance we need to traverse is 0.8. And remember that the maximum of the R just 1. So the points we are looking at are not local now. So, and one can ask now, okay, then just fix R, keep the points local again. Well, this time, to find the point in this smaller sphere, the points in that smaller point is, if we define the n to be total number of sample points, is the n times 10 to the power of minus 40. So we will need very huge amount of data to find the point in this local sphere in 20-dimensional space. So to conclude that the KNN works in lower dimensions very quite good, but in higher dimension it explodes. Now, doesn't there a method for reducing our dimension? Actually, we have, which is called principal component analysis. Well, in principal components, we use it for if we want or need to visualize our data, we use principal component analysis, which is called PCA. Well, what PCA does that it reduces the dimension by minimizing information loss as much as possible. What I mean is that we have an example again. So we are all familiar with the Pythagorean theorem. We know that D1 is constant, and our aim is reducing the D2. But we can focus on maximizing D3 instead of focusing D2. So our occasion now is the direction, the W is the direction now, which maximizes the projection lengths. And if we do the calculations now to get the result, doing some derivative tests and also Lagrange multipliers, etc., we will end up with a simple solution, which is the direction is actually we are looking for is the direction of the eigenvalue of the covariance matrix. Okay, now we have an example now. Well, the data we have is handwritten digits. All the images consist of 900 pixels. So our images lives on the 900 dimensional space. And if we want to reduce the dimension to 2 with our principal component analysis, the result is very beautiful actually. We can see that the distinction between 1 and 0 digits are still clear in the first image. But sometimes, like the image in here, the lower right corner, the distinction between 3 and 5 just get lost. So we should keep in mind that we always have a loss in PCA. Okay, now before diving into our last theorem, last model, which is the logistic regression, we need some background again, which is the definition. One of them is convex function definition. Well, we define to be f is convex if for all the members in domain members, this below equation holds. Well, it doesn't clear, but since we just need the intuition, we can define it like if the number of valleys and hills if the total number of hills and valleys is less than or equal to 1, we can define the function to be convex. What I mean is that if we look at the upper image, we see that 1 valley and 1 hill. So our function isn't convex now. And if you look at the lower image, we see that our function just consists of 1 valley. So it is convex. Also, we need the intuition of gradient descent algorithm. Well, how it works is that we use gradient descent for getting the minimum of our function. Well, it takes the gradient of the function, which gives us the direction in which our function increases the most. And if we multiply with the minus sign, it gives the direction our function decreases the most. And if we move along these directions all the time, we will end up eventually in the minimum point. So we have an animation again. But this is an example of not convex function since it consists of 2 valleys and 1 hill. And we have a convex function example. Now, if we use our gradient descent algorithm in this not convex function, there is no guarantee that the minimum we found is the global minimum. In here, we find the minimum, but it is the local minimum now. We miss the global minimum. But if we use it in the convex function, it guarantees us that the minimum we found is the global minimum, as in this video. We turn to our slides. Okay, we are ready to discuss our final machine learning method, which is the logistic regression. Well, to simplicity, we have just two classes in this example. Well, our assumption is that okay, let's suppose we have blue and red points again. So our class is blue and red. The product of being blue is, which has the equation this. Okay, sorry, I skipped a part. Okay, our assumption is that the product of being blue is in the form of sigmoid function. Well, sigmoid function has the shape of S. It looks like that. Now, the product of being blue is just 1 plus e to the some projection. So, and product of being red is just the 1 minus product of being blue. Now, we are trying to find the W, which is our parameter, which maximizes this likelihood loss function. Well, in here, we get our likelihood loss function in the logarithm function, which doesn't affect our answer so much, because it doesn't affect our answer since we are looking for the argument which maximizes it, and the logarithm function is strictly increasing function, so it doesn't affect our calculations. Now, if we do the calculations, we will end up with this, again, ugly-looking equation. And there's some bad news, which is this equation doesn't have a closed form solution. But if we investigate it a little bit, we see that it is a convex function. And so we can use our gradient descent algorithm now. And if we use it, okay, now our final equation. If we'll use it. So in this video, we use the principal component analysis at the first. We are trying to find the direction which maximizes the distinctions. So we find the direction. Now we will use the logistic regression now. The adjustments in here are done by the gradient descent algorithm. And it will decide the sharpness. Okay. So, as you remember the handwritten digits, if we train our logistic regression method with this training set, we will end up with these decision boundaries. The yellow and the green lines are decision boundaries. So it works very well actually, as you can see. So that's the I intend to talk. Thank you for listening. Questions? I have a